a good is delivered by Valentin Lychagin. I hope you all know the title, and one technical comment. There is a number of long formulas in the talk. The speaker will refer to the number of the corresponding formulas, and you will find the formulas themselves in the file which is put under this reference. It is on our website, and you can, I advise to open this file and keep it open during the whole talk. Now I pass the microphone to the speaker. Valia, you're welcome.
Да? Я вот забыл делать.
Ну, ты можешь заступить сюда.
Нет, это вот эта штучка где она должна.
Ну, главное, чтобы вот этот флакончик у тебя где-то недалеко. Это не отвалится.
Надеюсь.
Все, let's begin.
Let's begin, yeah. Алекс, сколько там человек? Сколько слушателей?
Да, пока будет.
Окей. Yeah. So let's begin.
Let's begin.
I will talk about very old mathematical theory. It's beginning middle of 19th century, and it was devoted first to solution of these equations. So at first it was a question how to solve such equations if it's simply function in three variables. So how to find x, y, z to satisfy this equation. And at that time, it was some problems with computers. So they used geometrical methods to solve such equations. And I think it was some, I don't remember, it's in the middle of 90s, they study this equation in the following form. They say when this function can be transformed in the function of the form a of z equal b of x plus c of y. Then in some sense you can solve just in one variable equations instead of three variables. And if I remember correctly, it was Saint Robert who proved the following theorem. So if your function satisfies this condition, then it can be transformed in this way. Nowadays, it has a lot of names. It's called Chern connection. It's called Lychagin connection, and etc. There are a lot of names. Really, it's some kind of connection, but from this point of view, it's not visible where is connection. Connection of what?
Repeat, please. I understand. You have equation.
Yeah.
So the second equation, what is the relation with the first one?
F equal. Okay.
Да, Валь, вопрос, как А, Б и С с F связаны?
А, Б и С F не... It's simply transformation of this equation to equation of this form.
Окей. Ну, то есть это как бы разделение переменных.
In some sense, yes.
Sorry, I speak Russian. Sorry.
That's a class of equation which allow this separation.
Yeah, not a class equation, a class of functions. So it was first geometrical methods to solve such equations. So you can, if it satisfies this problem, you can change variables in general. It simply will be z, it will be x, and this will be y. So making transformations from this to this and this to this, you can transform this equation to very simple z equal x plus y, and you can write like this: x, y, this x plus y, and so you can see how to solve. So x, y, you just move it on the point, and this gives you x plus y. After a very short time, namely in the beginning of 20th century, in 1920, I guess, because it was very important talk between Bляшке and Thomson. So they noted, maybe not everybody knows, but on the surface in the space, there is three directions, and they give you three foliation on the surface. And Bляшке and Thomson discussed this problem and found conditions when these three foliations will be like this. Is the one foliation, it's another foliation, and this is the third foliation.
So this condition says what? So this condition is equivalent.
Equivalent to this, but for some functions that you should recognize this function. If you have surface, you should be able to construct this function or something similar.
So if this condition is satisfied, you can find three foliation.
No. If you have three foliation, from these three foliations, you can construct this function and check this condition. And if it's condition satisfies, then you can find coordinates such that your three foliation will be these parallel lines. So, and this is the time, it was just simply geometrical picture, but they suggested to call this 3 web. In the sense that if you have some number of foliation on the plane, say one foliation, another foliation, the third foliation, the fourth foliation, and so on, you have, say, D foliations. And this you will call D web if all these foliations transversal to each other. So when they in general position. After this, Bляшке and his students, they start to study these webs of these foliations in more details. So they found a lot of interesting phenomena, wrote some number of books about this. And after Second War, Bляшке visited Soviet Union. It was international conference where he met Israel Moisevich Helfand together with his aspirants, and gave or presented the book. Now it's very famous book about geometry of webs. by Lychagin. And it was it gives some momentum to develop web geometry in Soviet Union. The book itself was translated by Akivis, and Akivis really was maybe the main person in Soviet Union who developed this web geometry. And now I should say some words. Really, I plan to do it on the first page of my presentation, but because I cannot show presentation technically, it's my talk is just some survey of possible paper devoted to Akivisu and Goldbergu. They were my colleagues and my friends and etc. And we did some more or less, not less important impact in this theory. It's called.
Из тех слов, что ты произносишь, я понимаю примерно 1/4. Я имею в виду, сказать, громче говори, пожалуйста. Я понимаю.
I will try. You just 1 millimeter from me. Yeah. Okay. Anyway, so what I wanted to say that it was very strong influence on my mathematical knowledge from Akivis and Goldberg. And really, this is slightly different vision on the web geometry. Usually, people who work with web geometry, they use classical differential geometry. And what I will do, what I will present, is how to use jet geometry for this. And it will be essentially simplify main construction is web geometry. Say there is some very old and very important problem. It's about linearization of webs. So you have simply some number of, say, d-web, defoliations. And you can ask, do we have diffeomorphisms that will transform all these curves into straight lines? It's a problem that was posed by Lychagin and solved by these two guys and with my participant also. Now, let's go to more formal stuff. So what I will think about GDEq. It will be just collection of functions, d functions on R2. And once more, we will assume that these functions are in a general position. So if you take dfi on dfj, should not equal 0 in domain of consideration, certainly, when I is not equal to j. So geometrically, it's corresponds to the scales, but I give functions, not foliations. Relation between functions foliations given by gauge transformations. We can substitute function f by phi of f. Phi is just some, strictly speaking, you can say that phi is diffeomorphism of the line of functions with non-zero derivative, if you wish. Then the class of these functions really will define foliation for us. And together with this transformation should really establish this correspondence between functions and foliations. We have also action of the group of diffeomorphisms. I will put two. It means that diffeomorphism of the plane. They also act on functions and on foliations also. So we have this action, is the first, is the second, and there is the third one. It's action of permutation group SD. It's simply on functions, yeah. So we can simply renumerate this sequence, and it's also give us the same the same family of foliations. So so from this point of view, what is the geometry of these webs? You can think that you have this families of functions with this condition, and you have action of these three groups. I will postpone to use this group, but we'll consider this and this. So this, as I explained, give you instead function, give you foliation, and this is just action of the diffeomorphism group. And now geometry, what kind of geometry? We should just follow, say, Klein point of view. We should study invariance of action of this pseudo group, really. And how to do this? So we consider bundle. And on this bundle, we have action here, action of pseudo group of diffeomorphism, local diffeomorphisms. And also we have action of this pseudo group fiberwise. So point transformations in this bundle. So you can think that here we have the coordinate U1, UD, X and Y, or X1 and X2. And this is projection on X1, X2. So then you can think about web as a section of this bundle. And because we not care about these functions themselves, we think about only foliations. So it should be not web, not this section, but together with the orbit of this section under this group and also under this group. In this interpretation, it's much easier to say what we mean, say, by jets or derivatives of our webs, because we think about them as a section. So we can take this bundle, take jets of sections of bundle, and after they will use the standard methods to study invariance of such sections. But
you skip the permutation group, yes?
yeah, really, permutation group commute with these two. So it's enough to find action invariance of this action. After take simply averaging or just consider action of this group on invariance and take means, and you will get all invariance that corresponds to this action. Okay. I will make one step more. Really, this is x1 and x2 is just simply some coordinates on the plane, but we consider up to diffeomorphism. So it means that maybe we can reduce our problem to problem only of this pseudo group without this one. To do this, we take this section, but consider as a surface in space RD. It's just two-dimensional surface in this d-dimensional space. Formally, you can say something like this. Okay, take this web and take this the first f1 and f2, these two functions, and because we have this condition, at least locally or in some domain, we can think that it's simply coordinates on the plane. Let's denote this by x and this by y.
Wow.
It was x1 x and y. Then geometrically, this section, it will be just some surface where this is x1 and x2 are coordinates. But now I will change its point of view and I will use this coordinates on the plane. Then I will get slightly different picture. I have this d-dimensional space and just surface inside of this space. And certainly I can play with these coordinates. Say I can take the first few functions as the coordinates. I can take the last these functions or some any pair of functions they can be served as the coordinates. So this is where we should really apply this group, just to equalize choice of this as a xy and another choices of functions, another functions as the coordinates on the plane. Okay, so I will just change my mind and will say that what is a d-web for us is the following. So we have t-dimensional space. We consider two-dimensional surfaces here with conditions that if it say it has coordinates, say u1, ud, and if you take here surface, the condition is the following: that if you take the surface and project on the plane, say 1, 2, on the 2, 3, and so on, it should be diffeomorphism because of these conditions. And now we in situations where we should study jets of two-dimensional surfaces in d-dimensional space. It is a classical object in geometry of jets. And now what we have in what kind of action we have here? This is not essential at all because its surface doesn't mean that it takes surface with coordinates. It takes surface of geometrical objects. We don't care about
X1 and X2 disappear.
x1 and x2 disappeared, yeah. Instead of them, we will use this xy and x and y for f1 and f2. It's the first one, and the second, our action will be very simple. I should forget this action and consider only this gauge transformation action. So we have the t-dimensional space, and you can just make transformations of this form. And to answer on the question when, say, one web equivalent to another in the sense that it can be transformed by this Hilda groups to another, it simply means that we should study invariance of this gauge action on this space. And actually, you see, the group itself, it's very simple. So you can expect that answers will be not too complicated. It's not completely true, but something similar we will do. Okay, maybe I will put here tilde because I will need also U in other settings. So I take the surface in ID and consider projections on the first and second the plane with U1, U2, and it gives me the following bundle. A, D, to R2. So it's point that's simply this U1 and this is U2. And in this setting, the action of my gauge transformations, yeah, it's this still this gauge here, but it's also gauge on the base.
So it actually means that, well, initially you consider jets of two-dimensional submanifolds.
Right.
You fix one by choosing these coordinates and declare it as independent variables. And
Yeah.
so it's a local.
It's local representation of the surfaces. So the surfaces will be just one small sections of this new bundle. But so in some sense, I have x, y, and only U3, UD. This is fiber-wise coordinates in this bundle. So the transformations, we have here transformations that just gauge and also gauge transformations here. I just will take a very simple case. We have, say, three-dimensional space, say, with coordinates x, y, and u. And we consider this bundle. And in this bundle, we consider a gauge in u. So we consider action over u goes to phi of u. So if you take infinitesimal vector field that stands behind of these transformations, you will get something like phi of u d du. Not phi, but psi.
DU.
Oh, sorry. DDU. It's a vertical vector field here. This vector field. Psi DDU. And this transformation, they correspond to shifts along this vector. And let's ask, what is the invariance of this action? And it's easy to see that if you take, say, ux and we'll divide it by uy, then what happens under this transformation? This doesn't matter. So it will be multiplied on derivative of phi, and it also will be multiplied on derivative of phi. So it means that this expression, it's invariant.
Would you check it explicitly?
Agree?
Miracle.
It's miracle, right? You see, we spent how many? 30 years or something similar to be able to make such computations. Okay, so what was essential for us that this guy it's invariant of this gauge transformation in this space, but it's invariant of the first order. How to get invariance of, say, second order, third order, and so on. So let's take total derivatives, GDEq and GDY. Obviously, they commute with this gauge transformation. So it means that if I take this invariant and take derivatives of this invariant, I simply, and it's compute, I simply will get all possible differential invariants of this gauge transformation.
How do you know that all? Because of dimension.
Just the commuting dimensions. So it's a trivial remark, but very important for future, for at least my future. What I will do now, I will back to this picture. So this is so the first two, it's also E1 and E2, but we will use XY. So this is our bundle, and here we have this gauge transformation, but gauge transformation acts on each U separately. So if I want to see invariance of this, it's also very simple to say. You should take these expressions and use them as the new coordinates instead of this U. Then I will simply remove action of my gauge transformation, at least on this part.
Ну, what number?
I will take these functions and will denote them. I am sorry for this. It's more convenient to denote it by UIs. On the first step, I will use VIs, but after a couple of minutes, I will simply remove two UIs. So instead of these coordinates, I will use now space where I have this bundle of D minus 3 cross R2 on the R2. And instead of this, I will use these coordinates. And it means that my gauge transformations will be very special. They will act only on X and Y and will not touch this V1 or V3, VD. Just because we fix them as the invariance of this action. So this our it is technically it's the more I think the more right way of doing all this construction. So we have this space once more d-dimensional. I simply changed this two coordinates, but now my gauge transformations is this simply transformations that produced by vector fields. And if I want to see what happens with, so let's call this bundle pi. So if you take k jets of pi, we expect to have some invariance. Then we should simply lift this vector field in this bundle pi. And now we'll just look at on the formula 3. Oh, I forgot about formula 2. Okay. Yeah. Formula 2 is for show you relationship between webs and certain Hilbert problem. Okay. So this is formula 3. Give you lift of your vector field. This is vector field Z. This vector field Z. And when you lift this vector field on this bundle, it will be like this and plus, and now you should say how this act on UD. You simply should check it how this act on transformation and XY, how they act on this ratio, and it's very, very simple. At least this form, this expression I can write. I don't want to produce new letters, so forget about this U. It's this really. So I substitute here V and U.
Prime means derivative.
Prime is derivative, yeah. It's derivative in Y, and this is derivative in X. And this is sum E from 3 to E.
UI means VI.
Yeah, and UI means VI, right? So this is vector field, and it's vector field X, Y on the plane, and this is just linear transformations in the fibers VIs. Okay. Now, what we can say about prolongation of so this vector field here on this construction, and we now should prolong in the K1 and the Kj's of our bundle pi. The formula, next formula, number 4, give you expression for this lifting, for this prolongation. And just look at that prolongation has very simple expression. It's the only that I forgot to say what means xi and theta I. Yeah, it means the following, that you should take correspondingly x in degree k or x in degree I and y in degree j, and write this prolongation, then it will exactly vector field psi I or theta j. So if you take L and take prolongation of this, it will have two terms. One psi I, that corresponds to.
What do you mean? X and Y are vector fields. What do you mean?
X and Y are functions.
No, X and Y are vector fields.
This function in X and this function.
Functions, yes.
They are functions.
Yeah.
And if you take prolongation will contain derivative of this function X and Y up to order K. So how to find coefficients? Say you have something like X in degree A of X and on some vector field, and plus so on. So this is how your prolongation will look like. But so how to get this term? I take simply this capital X equal to X in degree L. And then when I take the derivative, this term will disappear, and I will get some vector field here. And this is exactly vector field that denoted here by zeta I or zeta L.
But it is the standard prolongation from J0 to
Yeah,
J.
right. The simply it's very difficult to write general prolongation of general vector field. Yeah, it's there is some formula, but it's not very well applied, very well visible what really terms how they will look like. But because we know that it depends on these functions in differential linear way, then you simply should take functions of this form, and they will just give you the necessary coefficients with the derivative. What about this? this vector fields, they say psi I and theta j. This is two types of fields that presented in formula 4. They are vertical vector fields in our KZ space. So GK, and here projection on G0. So this vector field here, and this also here. And because they correspond to what I said, coefficients in X in some degree and Y in some degree, this set of vector fields give you Lie algebra. And this is nilpotent Lie algebra. And if it now, because why are you doing all this stuff? Because I want to find invariance of this action. And now how to do this? We have this two types of vector fields, one that corresponds to X, another to Ys. It's two nilpotent Lie algebras. They mutually commute. And we should find invariants or orbits of this action.
So do you want to find an analog of this invariant, but in your situation?
In some sense, yes. They will be a little more complicated, but it's what I want to say is that really computations of the invariance of order k, it means that I should find invariance of or orbits of these two nilpotent Lie algebras. It's not easy to say how to find them. Formally, it's at least formally it sounds extremely simple how to find invariance. Okay, take exponent of this vector field and you'll get invariance, but it's not so easy. Okay, but one important remark we can make immediately. It's what is the dimension of this orbit, and the dimension of this orbits, or more correctly, codimension of this orbits, it's exactly number of independent invariants. So in this case, it's easy to compute, and you will get the following expression: d minus 2 k plus 1 on k plus 2 divided by 2 and minus 2 k plus 1.
So this is the dimension of orbits of which action?
Of this action. What is given by these vector fields?
Of the list of
Yeah. So it's the first and the second. It's show us how many invariants of order less or equal k we have in this problem. But formula just this is really formula number 5, and there is formula number 6 that show you how you have how many invariants of exact order k you have in these problems, and so it's so-called Gilbert function. It's this formula 6. So k plus 1 on d minus 2 and minus 2k and minus 2. This is where k bigger than 1. Why k bigger than 1? Because when k equal 1, we have only these vector fields. It's just simply scaling in each fiber. So then invariance will be easy to find. Okay. No, so but it's computations that show us how many invariants we really expect on each level. On each level. First, some general remark. So if you have, it doesn't matter what this P is. You have this speed jets of P, you have action of some pseudo group. In our case, it's a very simple pseudo group of this form. And we are looking for invariance or orbits of this action. And let's denote it, say, by 5K, the orbit space. There are we need some technical conditions of the pseudo group under consideration, but for this case, you can easily check that this guy, so this is quotient of our action, but this guy will be algebraic manifold.
For our pseudo group.
Yeah, for really practically for all pseudo groups that which are algebraic in the sense that they produce algebraic actions in the fibers. It's so-called Rosenwick theorem. Also, all these transformations that preserve Cartan distribution, so you can get a quotient here. So it will be algebraic manifold together with some distribution there. Our construction looks like this. So if you take projection of this, you will get here also this manifold with the level k minus 1 and with the corresponding distribution. And it means that our quotient, it will behave like defined. Really algebraic defined, because all these quotients, they're just algebraic manifolds. And what we found, what we discussed, it's simply
roughly speaking, phi k are spaces of orbits. Yes?
yeah.
So you,
It's spaces of orbits. They algebraic variables. More, these algebraic variables are variables with singularities, and singularities correspond to singular orbits here. And regular orbits, they corresponds to smooth points on this algebraic variable. So this is really what we have in our hands. We have this chain of algebraic variables. We have with these distributions. So it's some analog of infinitely prolonged differential equation, roughly speaking. And invariants that we're looking for, they just simply can be considered, if they independent, they can be considered as coordinates on this algebraic variety. So this is simply what we put it here. It's simply a number of differential equations in order k. Okay.
And what about degrees of this phi k? I mean algebraic degrees.
Oh.
They grow.
You mean dimensions or what?
No, degrees as algebraic. If you locally.
Good question. I am not sure that. You see,
So you locally.
We have here we have here affine structures, and all transformations that preserve affine structures. So it will be affine bundles.
Yeah.
So it's I'm not sure. I don't know how to.
Okay.
It's what I will say that it will be just fine bundles of one algebraic right over another. What about algebraic degree? I cannot say. Okay, but what is my plan? I just will take at least I computed all this stuff for 3 webs, for 4 webs, for 5 webs, and stop it because lack of time. Okay, so let's do the first steps in these computations and see what they give us. By the way, in standard or in classical web geometry, when they call about invariance, they mean so-called relative invariance. They're not strictly speaking invariance, they will be multiplied by actions. Relative. Huh?
Relative.
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 Okay, so let's take the case that maybe the easiest, or to be honest, is the more difficult case. Oh, not sorry. D equals 3. So in this case, we have 2 invariants Q and P of the first order, or not all on the second order. And in addition, you have 4, I guess. No.
Give us the number of formulas.
It's number 7. It shows us this P and Q invariance. And also we have this double V1, double V2, double V3. This is invariance of the next order. It's 4th order invariance. It's really just see. This is the 3rd. Oh, sorry. It's the 3rd order. I'm sorry. It's 3rd order in this jet notation. In terms of webs, this is 4th order invariance of webs in original in functions, because you remember we just make this when we change it ui's and vi's. It's really vi's, they were derivatives of this.
Mean by order, degree,
Not order, differential order.
but P and Q are of
So,
third order.
yeah, this 3rd order, yeah.
And we want, yes, 4th order.
And this 4th order.
Mhm.
So it's easy to check that it should be relations between this. Yeah, we can how we can continue. It's now this is so-called Lie theorem. It says that you will get some number of invariants of sort P and Q, some number of these variables. It's like in jets, we have some coordinates, say X, Y, and G, this base coordinates, and some coordinates U as a fiber coordinates. So this is play role of the base coordinates, and this is fiber coordinates. Now we can take trisset derivatives of this. dv double vi on dq, or say L1 r dp L minus r. So you can take trisset derivatives. It also will be invariance. This is the important property of trisset derivative. If you take derivative of invariance by invariance, they will get invariance once more. They will be higher order, but differential higher order, but they will be still invariance. And because we know this number of invariants in each independent invariants on each level of this one, then, by the way, if you take the 3 here, it will be k plus 1 minus 2 will be k minus 1. Right. All right. Maybe not.
This is correct, but why?
Oh,
Why I don't understand why the derivative with respect to Q is R and with respect to P is L minus
it's
2.
no, it's L. It's derivative for the L. So we take R times in Q and L minus R in P.
Then there should be
This is
L plus
symmetric.
R.
This is symmetric.
L plus
So it will
Yeah.
what?
Ты написал матрицу, да?
No. This is of this type of it's just simply if you take 3C derivatives, so some expressions like this. So Lychagin theorem claims that you will get integration functions of this, you will get all invariants. So in the case of 3 webs,
But I don't understand. You have W, what now? In your example.
not number functions, invariants.
Three functions.
Yeah.
And you have 3 derivatives.
So yeah, I have 2 variables like base variables. I have 3 variables like fibrous variables. And now I will take derivatives of this with respect to these guys. But 3C derivatives because it's functions on the jets. It's not simply.
But what is L here?
Huh?
What is L?
It's this will give you an invariance of order L plus 4. This is invariance of order 4. And when I will differentiate, each differentiation jump order on 1, so it will be invariance of order 4.
In a sense, when you consider preset derivatives, P and Q become independent variables.
Right.
You in the invariant setting, when you choose invariance as coordinates, the first 2 become so to say X and Y, and well, but I'm afraid that
So
whether
you have many derivatives.
yes,
Yeah. Infinite number.
Object.
Yeah.
Well, I'm afraid that in formulas 10 and further on, you forget about P, and P becomes Q1 and Q becomes Q2. Yeah,
I'm sorry.
Yeah.
Yeah,
should be.
it's also Q1. Yeah.
Uh,
Oh, I see. Yeah. It's true. Yeah, I'm sorry for this. Yeah, but so the formula 9 shows what kind of syzygies these relations we will have. This is omega ij. It means that we should take omega I and differentiate in j variable. So it's so in other words, differential equations or syzygy, they will be first order because they contain only first order 3C derivatives.
Once more, I don't understand. Wij is what?
It's if it's Q1 and this is Q2.
Yes. So yes, we have first order equation.
Yeah, and what
Quasi-linear.
yeah, quasi-linear, and it should be 3 equations. Now it's problem for me also to recognize what this formula really mean without words, without some letters. Yeah, but this is ij with the upper index, its first equation, and aij with the top, the 2 on the top is the second equation. And I think that's all.
And what A0 means.
What is A0?
In Formula 9, you have A0.
It is a free term. It's just, it doesn't, it means A0.
Well, it not very important. Some rational function.
I can say more about these expressions if you will allow me to use my. It means the first CZG, the first equation, and A2 is the second equation. All of them has this form, the quasi-linear or linear.
So this 17 and 18 are 19 in between.
I think that yeah, I should ask for excuse. All this formula I got before vacation, and I did not look on them during vacation. But essentially, the following: that all these equations, they just quasi-linear first-order equations. So, and really, how you can formulate the result. So, really, all of this is a prolongation of these equations. So, really, the orbit space, at least in the situation when in domain where this is two functions, they are independent, because we can take all the derivatives where these functions independent. So in this domain, all these orbit spaces, they just prolongation of these first order equations.
So it's not generally defined, it's actually infinitely prolonged equation.
Yeah, yeah.
The first order.
But it's in what defined? It's defined really, because I take only chart where they depend. If I just will change these variables, it's like algebraic manifold. You can find rational coordinates, but in some domain, one rational concept, another rational concept. Okay. The same phenomena for webs. And really, in 4 webs, we have one invariant of order 0. Where is it?
Well, indicate.
It's number 19.
19.
Yeah, it says that we have one invariance of order 0, it's HF0, one invariant of order 1, HF1, and 2k invariance of order k, where k bigger than 1. It's this. And once more.
So on page 2, we have the complete description of our system. In the case D
equals 3. And beginning with the formula number 19, we have 4 webs.
19 relates to 4 webs.
To 4 webs. And here we have another P and Q, and we just look at on this. Q is a 0 order invariant, and P is first order invariance. This now we have these four functions that derivative of this will just generate all invariants really, and really in this case there are explicit formula for CZG for these equations.
In a sense, all webs are a bit simpler than
yeah,
and five. So
and five more simpler.
is even simpler.
Yeah, it's because you see, this is formula 21 and 22. They give you these equations, and after this, once more, this guys will simply prolongations. Once more in the domain where P and Q independent. So our quotient will be just simply prolongation of these equations. And finally, formula 23 and beginning 24, it says that we have two invariants of zero order. It's simply ratios, but it's clear from our vector fields. If you remember, they are scaling in fibers. So ratio, say U on. Wow. Okay, it's V. So in dimension 5, we have x, y, and three functions, and they denoted by U, V, and W. And so we have two invariants of zero order, three invariants of order 3.
S1, S2, S3.
Yeah, and one invariance of order, it's order 2, I think. Yeah, it's order 2. So two, 3, and one extra. And once more, you have syzygies, relations, but okay. They will. I will. Do you have websites of your seminar?
Hmm?
Do you have website of your seminar?
Yes.
So I can simply give Alec the draft. They can find.
But we have your presentation. You send it to me.
Presentation is not easy to read.
Okay, then send.
You should go line by line. Okay, doesn't matter. So
what is R? Formula 26. So we have 2 in order 0, 3 in order 1, and what is R?
I is invariant of order 2. And 1 invariant of order 2. That cannot be covered by derivatives of order 1. So really, in order 2, we have 3 set derivatives of invariance of order 1, and plus 1 extra. It's R.
And equations. I mean.
Yeah, there are some equations, but they're very long.
Okay.
Yeah. But what I wanted to say is that in all these cases, this quotient is behavior like differential equations and prolongations. And a final comment is the following. I just will illustrate this for case of 3 webs. So if you take 3 webs, so we have here this coordinates Q and P, and 3 V, that V1, V2, and V3. So let's take 5-dimensional space R5 with coordinates Q with a let, let's say. Okay. That let I will use the same letters for coordinates in R5.
What's up to you?
Okay, Q capital, P capital, W1, W2, and W3. And if you have a web, then we compute this invariance for this web. We will get functions that depends on variables, say x and y, something like this. So web really give you some So you have web here, three-dimensional web, and instead of this web, you'll get also surface in R5, and surface is the following. So Q is the value of this invariant Q on this web, P is the value of this P on this web, and so on. So it's given two-dimensional surface in R5. And now the theorem sounds like this. If you have two webs, and you have these two, let's call this a model or normal form. Then you can say that two webs equivalent under pseudo groups of diffeomorphism gauge transformations if and only if they have the same model.
Yes.
It's his answer. And by the way, this guy is solution of these equations that we discussed at first order equations. So it's not arbitrary surface.
Yes.
It gives solutions of the differential equations. Okay, I am very sorry for my talk for today because honestly, I prepared very detailed
It's fine.
presentation.
How does it relate to your old results with Vadim Goldberg?
It's related. In the following way. So it's with Vadim we analyzed problem of linearization of three webs.
Yeah.
With Goldberg and Akivis we analyzed conditions of linearizations of 4, 5, and so on webs. And what means linearization? Okay, it's just foliation. So web is just foliation on the plane. Assume that you have connection such that all this is curves are geodesics of this connection. Then when this curves will be straight lines, so when the problem realization will be solved, if you will find such connections that its curvature of this connection will be equal 0, this will be geodesics. Or in other words, it should be projectively trivial connection. On three webs, there is Chern connection. It's a connection where such that all it's called constructed by web, and this connection such that foliations will be geodesics. The only problem that this connection has curvature, and it was idea of Akivis. So take this connection and add some tensor such that this new connection will be trivial. You will get a differential equation for this quotient mark. Equations extremely complicated. It's overdetermined, very low. So this will be our really hard work, where we simply investigated conditions of solvability. So when you analyze conditions of solvability, you will get some number of invariants. Something should be equal 0 to get solvability on the first level and the second and so on. So and this give you a condition of linearization of three web. This is the same for four web and so on. But there is another way of doing the same, and it's more visible. It's the following, that you can try to construct this connection directly. So if you will write conditions for, say, for functions that satisfy the geodesic conditions, so there is just functions that leaves their variations, corresponding variations with geodesic, then this function satisfies a second order equation. And if you have an equation, coefficients in this equations will be so-called projective or Thomas coefficients of the connections that we are looking for. Number of these coefficients equal 4. So if you have 4 foliations, then conditions that all of them are geodesics will give you conditions for these coefficients, and you can simply define them by pure algebra, linear algebra. So it means that for web, you will get every time unique projective connection such that all these foliations will be geodesic. The only condition is it possible to do something like this? And it's called, I think, Liouville tensor. There is called Liouville tensor that you construct to show that your projective connection is trivial. And then solutions of these conditions of triviality give you just conditions for you will linearize this for web. The same for 5 web, 6 web, and so on. So because every time the connections that you're looking for will be given just simply from this linear algebra. This is why the case of 4, 5, and so on webs, it's much simpler than 3 webs. For 3 webs, yeah, you will get 3 equations, but for 4 functions. And once more, you will need to play this game because you have no connection. So if you will write a Liouville tensor and all necessary conditions for solvability, you once more will play this
The
game.
are undetermined for the 4-dimensional cases, determined
And there's, no, they also determined, because if you have 5 webs,
yeah,
and they consist of geodesics of some connection, then you take 4 of them, you will find this connection, and so it automatically gives us. So, and in our case, it's you can do just by using these coordinates on the plane. So all these conditions that we just talking, it's can be written in terms of invariance. But it's very long and very horrible formula for them. But say Bляшко himself, when he formulated this problem, he said that it's an unsolvable problem.
but please let's come back to the 3 webs. So you have this well, the last statement that you formulated about model equations. So if you have 2 particular webs, is it realistic to check whether they are equivalent or not?
Yeah, if all these computations are realistic, why not?
It is computed. Yeah, I mean, just practically.
Yeah, you simply should this invariance I gave you. You just take this, put it in these expressions. You will get simply these functions. You will get this surface, and you simply should compare, do they coincide or not.
And any simple conditions to check whether it's linear.
A linear, but linear.
In this 3 web.
It will be complicated because once more you will not get connection immediately, and you will get some extra terms. And also when you will write conditions, say that is projective flat connection, is give you differential equation, and expression of this unique coefficient in terms of another, it give you also differential equations. It will be overdetermined system of equations, and you should investigate where it will be solvable. So you should, in a standard way, prolong, and see some conditions that you.
You have your invariance. You take the simplest linear web, compute invariance of this simplest web, and then you say that
Yeah, so certainly, if you, yeah, you can do from different, completely in different point of view. You can simply take this model, such that constructed from linear web, but we have too many linear webs. So to answer, is this web is equivalent to some linear web?
yeah,
It's straightforward.
it's
But
simple.
it's simple, yeah. But to say I have three webs, do this web linearizable, I will involve once more in this game, this checking of solvability. Okay, so I ask for excuse for not so transparent. Yeah, and also I try to speak loudly. Dim. Okay. Yeah, that's what I wanted.
Just check whether you hear or not. Дай мне пятёк.
У тебя нет?
Да, Рубцов там. Я слышу, как он дышит. So thanks a lot. It's a good beginning for our order. So questions, remarks, comments. I hope you hear me. No question, no remark, no comment. Владимир Николаевич, ты здесь?
Нет.
Yeah, убег. Вино пить пошел. Okay, thanks a lot. So we meet in Zoom next week. Thank you for visiting us. Goodbye.
Йось, а что будет в следующий раз, значит, непонятно пока, да?
Нет,